To the ancients, it was known as the mouth of hell or the gate of hell. Today, we know it as geothermal. The word comes from the Greek word geo meaning earth and thermal meaning heat. Therefore, geothermal means heat energy within the earth that exists in reservoirs of hot water and steam, deep within the subsurface of the earth. Geothermal energy was commonly used among many ancient cultures around the world. Native Americans used hot springs for its healing powers as far back as 10,000 years ago. The Chinese, Romans, and Turkish are among the many cultures where hot springs were used for similar purposes as well as for bathing and heating. In modern times, geothermal energy was used for district heating in the late 1400s in France, followed by a similar district heating system in Boise, Idaho, in the 1890s. In 1907, Hot Lake Hotel in Oregon became the first known building in the world to use geothermal energy for heating. This was followed by geothermal heating of greenhouses and residential homes in Boise, Italy, and Iceland, where nearly 100% of its homes are heated with geothermal energy. The early 1900s also witnessed the rise of electricity production using geothermal energy, known as geothermal power. The first known geothermal power plant was tested in Italy in 1911, followed by the first industrial geothermal electricity production in 1958 in New Zealand. Despite its long history, geothermal energy remains underutilized due to a lack of investment and financing. In the United States, only 3.6 gigawatts of geothermal electricity, enough to power nearly 3 million households, is produced, accounting for 0.4% of total electricity production. 100% of U.S. geothermal power is produced in the western states, with California and Nevada contributing the most. Obviously, their tectonic nature gives them an advantage. Globally, a handful of countries account for 75% of geothermal electricity output. Geothermal energy originates from the original formation of the planet and the slow decay of radioactive particles in the Earth's core. To understand its relevance to geothermal power, we need a basic understanding of the Earth's interior formation. The Earth has 4 major layers composed of mainly iron, nickel, and silicate. These layers are crust, mantle, outer core, and inner core. The inner core is the deepest layer and is made of solid iron and nickel. The temperature at this layer is believed to reach up to 10,000 degrees Fahrenheit, which is as hot as the sun's surface. These extreme temperatures melt any solid materials. However, the intense pressure that exists in this layer changes the melting point of the iron and nickel mixture, allowing it to remain solid. The outer core is a hot molten iron and nickel mixture called magma. This layer is liquid due to the high temperature and the decreased pressure compared to the inner core. The mantle, which is a layer of magma and rock surrounding the outer core, is the thickest layer. Temperatures in the mantle range from about 392 degrees at the upper mantle crust boundary to approximately 7,230 degrees Fahrenheit at the mantle outer core boundary. The upper mantle is solid silicate due to lower temperature and pressure, while the lower mantle is molten due to higher temperature. Since the fluid at the lower mantle is lighter, it rises towards the crust through fractures and faults called tectonic plates found under the continents and ocean floors. Magma, from the lower mantle, comes close to the Earth's surface near the edges of these plates through the faulted or fractured routes. The lava that erupts from volcanoes is partly magma. Finally, the crust is the outermost layer made up of solid rock that forms the continents and ocean floors. The low temperature and pressure that exists at this layer allow the crust to be solid. Silicate materials make up over 90% of the Earth's crust, while nickel and iron alloys make up the rest. Scientists have identified 7 major tectonic plates along with many more minor and microplates. The plates drift apart and push against each other at the rate of about 1 inch per year in a process called continental drift. Continental drift creates faults and fractures in the crust. Most large-scale geologic events, such as volcanoes or earthquakes, also occur along these tectonic plates. More than half of the world's active volcanoes above sea level occur along the island chains that encircle the Pacific Ocean in an area known as the Ring of Fire. Regions along the edges of the tectonic plates offer untapped geothermal energy. For example, Two of the major moving tectonic plates, the North American and the Pacific plates, collide on the coast of California, creating a major earthquake zone known as the San Andreas Fault. The entire San Andreas Fault system extends over 800 miles long and at least 10 miles deep inside the Earth's interior, allowing the state of California to build the largest geothermal power plant in the world, the Geysers Geothermal Complex, which generates between 700 megawatts to 900 megawatts of electricity, enough to power nearly 1 million homes. Another region with tremendous potential for geothermal energy is the East African Rift System, where the African Plate and the Arabian Plate meet. The rift extends thousands of miles from Lebanon and Asia, past the Red Sea before turning inland into the Danakil region of Eritrea and Ethiopia, making the region one of the most active volcanic zones on Earth. Rain penetrates deep into the fractured crust and is heated by the hot rocks into a large, hot water and steam reservoir. A small portion of the hot water and steam mixture rises to the surface through the fractured rocks, creating geysers and hot springs. A straight pathway to the surface leads to fast-shooting waters, such as the geysers of Yellowstone National Park, while a less straight path leads to a slower flowing rate that turns to hot springs. In some cases, the slowly rising reservoir water mixes with the rocks beneath the surface and changes its chemical composition, leading to the many colorful acid lakes found in Yellowstone National Park and the Danakil region of Eritrea and Ethiopia. A portion of the hot water and steam, however, remain in the underground reservoirs, and this is the source of the geothermal power. This resource is extracted in two different ways: hydrothermal systems and enhanced geothermal systems, or EGS. A hydrothermal system is a naturally occurring system where rainwater that penetrates deep into the crust is heated by the hot rocks to create a natural steam reservoir. This system is limited to a few places around the world where there is a rich, naturally occurring reservoir of thermal energy at shallower depths of 2 to 3 miles. Enhanced geothermal system, EGS, also known as man-made geothermal system or engineered geothermal system, works by drilling 2 holes in the deeper crystalline rocks and connecting them by a network of fractures. Then pressurized fluid, mainly water, is circulated through the drilled holes. This technique allows for production from wells as deep as 6 miles. Harnessing geothermal energy for electricity is a relatively new and rapidly growing technology. The process starts with the completion of geological and geophysical surveys, followed by an evaluation of a production well for flow rate, temperature, and pressure before going into production. Geothermal power plants are categorized as dry steam power plants, flash steam power plants, and binary cycle power plants. Dry steam power plants use steam drawn directly from high-temperature reservoirs deep beneath the earth. Steam from multiple wells is gathered using a network of insulated pipes to a central receiving station and is directed to a turbine which drives an electricity-producing generator. After the steam condenses, it is cooled and re-injected back into the reservoir to be heated, and the whole process starts again. This technology is the simplest form of geothermal power plant. However, since naturally occurring stream reservoirs are limited to a few regions, dry steam power plants are very few around the world. Flash steam power plants use extracted hot water or a mixture of hot water and steam. The steam is directly routed towards the turbine for electricity production, while the hot water is pumped under high pressure into a tank at the surface. The tank is held at a much lower pressure, causing some of the fluid to rapidly vaporize or flash. The vapor is then routed to drive a turbine. If any liquid remains in the tank, it can be flashed again in a second tank to extract even more steam. This is called a double flash power plant and can be used to extract an additional 15 to 25% steam from the system. Flash steam plants are the most common type in operation today due to their flexibility in using low-temperature hot water as a source. Binary cycle power plants are utilized for much lower water temperatures. In this case, the heat from the hot water is extracted through a heat exchanger to vaporize another organic fluid with a much lower boiling point. In principle, heat is extracted from the hot water through a heat exchanger and transferred to the second fluid, known as a working fluid. The newly vaporized working fluid is then used to drive a turbine. This allows for the generation of power from much lower temperature production wells. as low as 170 degrees Fahrenheit or 76 degrees Celsius. In addition, since low-temperature water is used, artificial reservoirs can be created by actively injecting water into shallow wells to be heated and pumped back out. For this reason, a significant proportion of geothermal power in the future could come from binary cycle plants. In addition to generating electricity, geothermal energy continues to be used for other direct applications. More than half of direct consumption is for space heating, where heat is transferred to and from the Earth to provide cooling and heating for homes and buildings. Agricultural application, such as the greenhouse cultivation of vegetables, fruits, and flowers, is also another common use of geothermal energy. In post-harvest, geothermal energy is also used in the drying and dehydration of fruits, vegetables, and meat products to reduce waste and ensure food availability throughout the year. Geothermal energy is considered renewable because heat is continuously being produced below the Earth's surface. It is sustainable if an equal volume of water is injected back into the area where the heat extraction takes place. In addition, geothermal power plants produce electricity consistently regardless of weather conditions. They are also highly scalable, operating from a rural village to an entire city. The power generation is local and requires no lengthy and expensive grid system.